So another operation we can do on functions is something called a composition. A couple of housekeeping things here. First is that you're going to see a brand new type of notation. And that's this right here. I'll zoom in on that right there. It looks like an O, but if you see it in print, it'll look like a circle because it's actually a small circle and it's pronounced circle. So it's not multiplication. It is a new kind of symbol that we're going to need to get used to. Composition of function is something I like to call a function inside of another function. And this circle is pronounced circle. So this here would be pronounced f circle g of x. And what it means is that you're going to take this function g of x and put it inside this function f of x, where if you look at this right here, essentially you have a function f where the input is not just x, but a separate function called g of x. We can reverse these and put f inside of g over here like this, right? Again, this is going to be g of f of x is the way it's pronounced. And you can even put the function inside of itself, like f circle f of x is going to be f of x. The function here that's inside the parentheses, which I will recolor to be, let's say, orange. This is the second function that is listed in the circle notation. And it is also something I like to call the input function, because this is what's getting inputted into that. And again, just like with operations, we are making brand new functions out of these two separate functions. But finding the domain is going to be slightly different. The domain of a composite function, right, something that is composed, such as f circle g, is a combination of two separate functions. One, the composed function f circle g, and g, which is the input function. So essentially, the domain of f alone, the first function, doesn't matter. It does not matter for the composition, right? It's kind of built into the composed function. That's essentially why. But you do have to maintain that the domain of g, right? Because again, if a number or an input was not valid for g, that means that restriction is going to carry through to the composition. Right, so again, just to highlight and reiterate what I mentioned before was f circle g is what this is pronounced, has two functions listed here. One, the first is f, and the second is g. I like to call these first and second function. I also like to call these outside-inside function, right, where this is equal to f of g of x. And if we reverse these, then that means g is listed first, f is listed second, and then that means g is the outside and f is the inside. So this will be g of f of x. And once again, we can put a function inside of itself, f circle f, where both are outside inside. And this would be f of x. So let's work on some problems here. Here we have, let's move this up, f of x defined as 6x minus 5, and g of x defined as x squared minus 15x plus 54. So if we're looking at f circle g, what we are looking at here is f of g of x, which is going to be f with the input of x squared minus 15x plus 54. And what we talked about before was really whatever is in the parentheses here is what's getting input into our function. So if f is equal to 6x minus 5 as it's listed here, what we are literally doing is erasing this x and instead putting in whatever our input is. In this case, x squared minus 15x plus 54. Okay? So in order to evaluate this, let's do some distribution. We're going to get 6x squared minus 90x plus 324 minus 5. Don't forget, this minus 5 is coming from the right there from f of x. So this is going to equal 6x squared minus 90x plus 319. Saved ourselves a line there, so let's move b up. Let's compute f circle g of 4. Now, since we already computed f circle g, that means we can use this to input. But once again, be careful of this, because what we have here is the domain of f is all real numbers, negative infinity to positive infinity. So essentially, we don't really have a problem. We don't really have a problem with any of these inputs. And since they're polynomials that are coming out of here, we're not going to have a problem with inputs. But if there was a restriction for g, there's potential that it might not show up here. So while you might be able to calculate this, right, if there was a problem in the original function which could disappear based on your composition, that's something to be careful of. But again, with everything here being polynomials, that's not going to be an issue. So we can take 6 times 4 squared minus 90 times 4 plus 319. Work it out with order of operations, and 55 is our result. And again, computing f circle g of 7 is going to be the same thing. Sorry, negative 7. It's going to be the same thing just as plugging in negative 7 over here for x. Six times negative 7 squared. Remember, negative 7 raised to the second power is going to be a positive 49, because a negative times a negative is a positive. And this works out to be 1,243. So let's compute g circle f of 2. Right, computing g circle f of 2 means, remember, we did f circle g already, and we did not do g circle f. Those two are different. So let's take a look at what g circle f is going to look like. 6x minus 5 to the second power minus 15 times 6x minus 5 plus 54. Remember, our input function here is f of x. So that means we are taking this 6x minus 5 and substituting it for these x's right there. And that's how we get this large expression, which will have to be FOILed to get 36x squared minus 30x minus 30x plus 25 minus 90x plus 75 plus 54. Combine like terms to get 36x squared minus 150x plus 154. That's going to be 154. So again, what we have here is g of f of x. What we're looking to find is 36 times 2 to the second power minus 150 times 2 plus 154. What we're looking to find here is g of f of 2. And we can work all this out to get an answer that equals -2. Now there is an alternative. We'll call this method 1, which is evaluating g of f of x and then plugging in the value 2. Or we can evaluate g of f of 2 by first evaluating f of 2. Remember, f of x is equal to 6x minus 5. So that's going to be 6 times 2 minus 5, which is equal to 12 minus 5, which is equal to 7. And then we can take this input. Again, this is equivalent to f of 2. So if we want to evaluate g of f of 2, that means we are essentially evaluating g of 7. So then g of 7 is going to equal this with 7 squared minus 15 times 7 plus 54. So g of x with the number 7 plugged in. And we get -2 as our answer. All right, let's look at 2 more. F of x and g of x are going to be x minus 6 and 1 over x squared minus 9, respectively. So the first thing we're going to look at here is the composition of f circle g. Remember, f circle g of x means that the second function listed is the input function, which means we are looking at x minus 6 with this x erased. And in place of that x, we are inputting 1 over x squared minus 9. 1 over x squared minus 9. Which means we are going to need a common denominator. All right, x squared minus 9 is going to be the least common denominator, and that's going to get multiplied on top and bottom. So we're going to get 1 over x squared minus 9 minus 6 times x squared minus 9 over x squared minus 9. For a final value of 1 minus 6 times x squared minus 9 divided by x squared minus 9. Right? Do we have to distribute this and combine like terms? Don't bother. Let's leave it like that. Nothing's going to cancel out, so we're all good. So, this is what f circle g looks like. But what is the domain of this going to be? Right, in order to find the domain of f circle g, we have to consider and find out 2 things. Right, first, the domain of f circle g of this function here. And second, we have to find the domain of what was the input function, right? The function that was input into the other function, that is this function right here, g of x. So this one. So we also have to find the domain of g, and then we have to combine them together. This denominator, x squared minus 9, from f circle g, this cannot equal 0. So x minus 3, x plus 3 cannot equal 0. That means x minus 3 cannot equal 0. X plus 3 cannot equal 0. This is the 0 product rule. So x cannot equal 3. X cannot equal -3 either. Now, thankfully, take a look at function g. has the exact same denominator. So x squared minus 9 cannot equal 0. Since the denominator is the same, that means the restriction is the same. So in fact, combining these two domains together is just a matter of writing out the one domain, which is all real numbers from negative infinity up to -3, from -3 to +3, and then from 3 to infinity. And you put that in interval notation. And you are good. Again, from left to right. So let's take a look at these same two functions, f and g. And let's reverse this composition from f circle g now to g circle f. And we'll see how this differs. So again, we are taking g circle f, which means that we are inputting f of x into g, which means that we are taking this function g and inputting x minus 6. So 1 over x squared minus 9 is going to become, if we literally erase that x, it's literally going to become 1 over x minus 6 squared minus 9, which is going to become x squared minus 12x plus 36 minus 9 inside the denominator. Which means this function is going to become 1 over x squared minus 12x plus 27. And this is what g circle f looks like. So let's take a look at our domain. Remember, we need the domain of g circle f, this right here. And we also need the domain of f, which was given to us as x minus 6. Again, so thankfully, the domain of f is all real numbers. It was a polynomial. So that means we don't have much work to do over there other than recognizing it's a polynomial. And any restrictions we get from here is going to be the final domain. So x squared minus 12x plus 27 cannot equal 0. If we factor into x minus 9, x minus 3, that means we can find our restricted numbers. X minus 9 cannot equal 0. That means x cannot equal 9. X minus 3 cannot equal 0. That means x cannot equal 3 either. So again, over here, even though we're combining technically two domains, one of the domains is all real numbers. So our only restriction will be with these two critical values here. That's negative infinity up to 3. That's from 3 to infinity. Nope, not 3 to infinity, sorry. 3 to 9. And that's from 9 to infinity. And there is our function, and there is our domain. Let's try another one, number 3. Two functions here, h, radical 1 minus 2x, and p, negative 2x minus 4. So let's take a look at how radicals behave when they are composed. All right, this one a radical with a polynomial. All right, so h circle p, h circle p of x is going to be, p of x is the input. So that means we're looking at h, radical 1 minus 2x, with this input in place of x. So that's going to be 1 minus 2, and instead of x, negative 2x minus 4. And this is our radical. So let's work it out what it's going to look like inside the radical. Distribute that negative 2. 1 plus 4x plus 8. This is what's inside the radical, which turns out to be the square root of 9 plus 4x. And this is our function. It looks like we can reduce or simplify. 9 and 4 are perfect squares, but this plus sign is going to stop us from doing that. So instead we can finalize that this is h circle P, h of P of x, and we can go ahead and find our domains. Remember, the domain of a radical function means 9 plus 4x, which is this radicand, has to be greater than or equal to 0. And if we look at our other side, which is the domain of the input function, P is a polynomial. So, again, all real numbers. So 4x is greater than or equal to negative 9, because we're solving this inequality now to figure out the actual domain. Divide by 4, and x is greater than or equal to negative 9 over 4. So that means our domain on a number line is going to have a single critical value shaded in, and then greater than that all the way towards infinity. So negative 9 over 4 towards infinity. All right, moving along to our last one. Oh, I forgot to erase it. Spoiler alert. Well, you know what? I'll leave it and I'll just talk through it. How about that? So, same to h and p, radical 1 minus 2x, negative 2x minus 4. In this case, we are reversing p circle h. That means p of h of x. So h of x is the input. Radical 1 minus 2x is the input. Which means we're taking negative 2x minus 4, and we're getting rid of this x, and instead putting this 1 minus 2x radical in place of that. And that's what we have here. Negative 2x minus 4, but negative 2 times radical 1 minus 2x minus 4. And there's no more simplifying to be done here, so we can jump straight to the domains. We have the domain of p circle h, which is 1 minus 2x greater than or equal to 0, because that's the radicand. And then we have the domain of h, which is 1 minus 2x greater than or equal to 0, again, because that's the radicand. Oh, so it turns out these radicands are the same. Subtract 1 from both sides. Divide by negative 2, which flips the inequality. X is less than or equal to 1 over 2. And you're going to get the same thing on the other side. So our critical value is 1 over 2. Shade to the left towards negative infinity. And that means we have negative infinity up to 1 over 2, including that with a square bracket. And that is that for compositions.